just that. We could spend a little time on the remaining notes on beer and tea if you don't have questions, but I'd rather go to your questions and any further details you'd like to bring up on these first.
About white wine color, are there, what you said, I think, last time, are there no carotene pigments in white wine?
The carotene content of grapes even is quite low, and it's not been very well investigated. I believe Dr. Noble is or has been doing something on this, and certainly they're present. But compared, say, to many yellow fruits like the pineapple, the content is very low. And it's my opinion that lipoidal, the lipid content of grape juice, much less wine, or whole grapes for that matter, is quite low. In fact, the main lipid lipid solvent soluble material from grapes is oleanolic acid, which is a polyterpene, steroidal-like material. So that there just isn't very much fat, and it's my opinion that carotenes are much too low to contribute to color of wines, and the evidence is pretty clear on that point. The carotenes have a characteristic spectrum, peak around 460 generally, and it's a triple peak. Looks something like this, where this is about 460, and you don't find anything like that in white wine.
Possible, however, that the fatty acids produce flavor precursors or are flavor precursors that are significantly extremely small amounts, fraction of parts per billion.
Okay, I certainly wouldn't argue with you in particular in this regard. I didn't mean to poo-poo them, but I think in terms of aging at least, what's there is there when the wine is made, and it probably doesn't change much after that. And would you agree with that? That the generation must occur in the early stages as the wine's being made.
It's possible, though, that phenols are related to the formation of these follicles, so that it might be significant. Phenols not only in color, but also in the formation of follicles at that stage.
Well, that's right, and that's one reason, and a corollary reason that we're rather excited about the finding that when a phenol oxidizes, it produces a potent oxidant as a coupled product, because then this could go ahead and hydroxylate double bonds and do a lot of other things. So yes, you may well be quite right. On the other hand, I guess I'd have to say that there's, well, I don't want to give away any of their secrets, but Mr. Crow and Professor Guyman have just recently had a rather important breakthrough in the geranium odor of understanding the geranium odor from sorbic acid, and it's related to this kind of thing. And certainly it's a very recognizable and potent odor in small amounts, so that certainly can't poo-poo that this happens. On the other hand, the nature of the odors that occur just don't seem to me to be rather generally not similar to this kind of compound. But certainly I don't know. And in the case of the leafy grapes and the problem with tea flavors and so on, then it may well be that fats had a lot to do with formation of these compounds.
Have you done any experiments on the phenol content of mechanically harvested?
No, a couple of 3 years ago, we started to think about this, and what we did do was we took all the leaves off of 2 or 3 grapevines and weighed them and determined how much phenol there was in all the leaves on the vine. And then we did some other work which isn't completely digested even yet, where we measured the surface of the leaf and computed for these, we hope, representative vines of 2 varieties, how many milligrams of phenol per so many square inches of leaf surface and that sort of thing. So we had some basic data as to how much leaf it would take to make a significant difference in the phenol content, and it was fairly sizable. I haven't pulled this together even for a report, so it's not too clear in my own mind, much less published, but in general it appeared that you did get flavor effects, at least the level at which flavor effects were reported was lower than that at which you seem to get a significant change in phenol content. And there is a big difference in, it's just like extracting phenol from grape skins. You don't just put the leaf in and the phenols pop right out. You know, the leaf has to be either pretty withered or fermented for a period of time or so on before very much phenol comes out of it. So if you can get green, now dried leaves is another matter, but green leaves, if you can get them out fairly quickly, then whether they were in the must or not would make relatively little difference, just as if you get the juice away from the pumice fairly quickly, it makes relatively little difference. Other comments or questions? Yeah.
I'd like to hear, we had a little of this in 126, but we never really got into it in any depth. Could you explain what goes on when you take globular proteins like egg white or albumin or isinglass or gelatin, okay, and then go through the agitation, and then what happens once you get this form, this denatured form, as it's going through the wine and is related to contracting or trapping tannin?
Well, I wouldn't agree with your, you shouldn't lump everything together that you lumped there as a globular protein. As a former protein chemist, that's not quite so. But in any case, there seems to be a physical effect that is not too well understood. Like, for instance, you know, when you beat egg whites and make meringue out of it, then the beating produces a physical change in the protein that isn't too well understood in any kind of detail. But basically, it seems that you are tending to unfold the molecule into a more nearly linear condition. And the best example of this that's really rather well known is gelatin, and I think we showed the slide, which I can't draw as nicely, but we have a spiral. The collagen, which is the protein in hide, skin, and anything that converts to gelatin, hoofs, horns, what have you, fingernails, I suppose, is a rope, a three-stranded rope, where each individual strand is an alpha helix. No. Yes. All right, an alpha helix of the individual strand, and then each alpha helix, which is a peptide chain, is wrapped still further around the others. And I drew this once, and you find it awful hard to draw a spiral, but at least freehand. But what happens is that this three-stranded native molecule of collagen then breaks down to become one of these, and then this alpha helix, particularly in the collagen group, is not held together very well because the glycine, proline, and hydroxyproline are not strong hydrogen bonding units. The glycine is short and has no extra unit, and the hydroxyproline, proline are amino acids again with relatively weak hydrogen contributors. So this breaks down rather easily into a long, mobile, easily flexed single chain of amino acids. Well, this is gelatin, and the quality of gelatin has to do with how much hydrolysis there's been. In other words, the best gelatin would be the longest chain of amino acid with the fewest free amino acids or small peptides, and it's the best finding agent. On a weight basis, it's still one of the best. Remember, we showed you some data on that. And I think the reason it is one of the best, if you visualize you're trying to remove a tannin, which is a flavonoid polymer, probably at least a dimer and very likely bigger. It's a three-dimensional. The flavonoids would be crossed to each other. You know, if you're going to link the A ring of one to the position 4 of the other, they pretty much have to be at right angles to each other, otherwise they wouldn't lie flat, even though we draw it flat. And then if you made a third unit, it'd be at one of the other angles probably, so that it's a pretty spherical or at least a three-dimensional lump in the solution. So perhaps one of the reasons that gelatin does a really good job is it's able to curl around and complex with the OH groups very easily. So that this is the kind of thing I think that is involved, and the same thing would be true of casein or any other protein, egg white, to the degree that you can partially denature without hydrolysis to get the peptide chains extended and exposed to the solution, then the better chance you have to complex with the tannins, which by themselves are not all that flexible, not all that linear. So as best I can approximate it, that's the way I would express what you're asking.
Speaking chemically, this would be strictly a hydrogen bonding affair?
Mm-hmm. Yeah, that's pretty well proven. It is strictly a hydrogen bonding affair. Now, it depends on how you define strictly, but because it is true that on the oxidation type reaction, where we have already the quinone, then say this is a B ring, we can substitute in, well, since we'd substitute in an ortho or para position to one of the carbonyls, every position is an ortho or para position. So it's para here, and it's ortho there, and it's para, no, excuse me, that's ortho here then. So that every position would be subject to substitution with sulfhydrocysteine or with nitrogen from lysine or terminal free amino end of a protein. So you do get covalent substitution of this kind into the oxidized phenol ring, but that's a slower reaction. It involves browning already, and in the wine circumstance, I think that's relatively unlikely.
Well, it's the denaturation you're talking about. I'd like to ask you, I had a guy who was from Bordeaux tell me that if you're using, what he was talking about, but assuming it's the same type of denaturation, you shouldn't use a blender. He said use a whisk, you know, or they said because he didn't know why, but
it's a French chef type.
Yeah. French chef. Would you know something on a blender perhaps physically, mechanically, perhaps make?
Well, it's possible. After all, a rubber band is chemically bonded isoprene type units. If you pull it far enough it snaps, you've broken mechanically bonds, you see. In other words, you're producing a chemical reaction by physical means. And I suppose you could, certainly the shear reactions do break the peptide chains, so that may be part of what he has in mind. It is true that if you use a very high-speed colloidal mills or what have you, sufficiently long, and you can, by the shearing forces, produce peptides instead of proteins. But I did a fair amount of work with alfalfa protein where we isolated it from the alfalfa with a colloid mill, and it takes a whale of a lot of grinding to do very much protein breaking. I think probably what's in his mind, and the same reason that in cooking they make the distinction between the whisk and the heavy whipping, is that once you've produced a meringue-like condition, this foam with air in it, then you aren't going to get that dispersed in the wine or in cooking, so that you end up with blobs of meringue floating on your wine instead of proper dispersal. So I think it's just an application difficulty that he's talking about.
Well, one last question on
Okay.
this, and that is that isinglass, at least supposedly in this group of proteins.
It is.
Can you explain the fact that as far as brilliancy and clarity, this has a reputation of doing a better job?
Sure, it's easy to explain. Isinglass originally is sturgeon bladders, and it's fish gelatin. Now the fish gelatin, the collagen of fish, is notably, gelatin has what's described as a, what is it? There's a special term for it that escapes me right now. But anyway, there is a special temperature at which these natural collagen fibers will break out. It becomes almost like a melting point. It's a rather precise temperature at which these will separate. And in the fish gelatin, they're cold temperature animals, you see. The melting point that breaks down the collagen is much lower. Maybe it's, well, offhand, I have seen figures. The typical pig skin gelatin is about 60 degrees centigrade, and the fish gelatin is about 30, as I remember it, much lower anyhow. So there's two factors then. That first of all, the old-fashioned isinglass, which was sturgeon swim bladders, well, this is a pretty pure tissue to begin with, almost pure collagen, not much contamination, whereas pig skin isn't all that clean or uncontaminated. Then this low breakdown means that there's not so much risk of hydrolysis, so that you end up with a nice long chain with no trouble. You can break it down without sufficient heat, whereas with pigskin you get, due to the heat, some hydrolysis. So that's the reason that Isinglass has this reputation only because it does make nice long linear chains with less trouble than pigskin. And the pigskin gelatin can vary all the way from quite good to pretty bad, depending on how drastic it's been treated in the making of it. And since a lot of the gelatin, most of the gelatin today is made for Jell-O type puddings and so on, where all they want it to do is to gel with water, although gel strength has a lot to do with the longer chain gives the greater gel strength. On the other hand, you can get gelatins too strong. You know, you try to eat it and it's like so much rubber eraser almost, so that they want some breakdown in the gelatin. And so as a consequence, the thing that makes it good for food value is not so good from wine fining. And wine fining is a pretty small market for gelatin, so they aren't nearly as careful as they might be. It used to be that Swift and Company, I guess it's S-Mark today, used to send an exhibitor to the ASE meeting. They don't do it anymore. I guess they just don't feel there's enough market to. They still have the products, but they're not really worried very much whether they lose the market. Jeff, you had a question?
I was going to make a comment on that whisk. The original use of the whisk was in a copper bowl. And the copper bowl, as soon as you start feeding a protein in a copper bowl, if you know anything about chemistry, you can put two and two together and find out what's happening. And the French are still stuck on using the whisk when they lock the copper bowl.
I see.
That was the original use.
Well, I wasn't aware of the copper, but I think we'd like to keep the copper out of the wine in any case. So, okay, should I go ahead with some of the beer and tea comments then, and if other things come up to your mind, or would you have some other points you would rather raise? Okay, well, some of the beer comments relate to our fining, and that's what you're mainly asking anyway. I don't think we need to spend much time on the beer consumption. We've already made the point that beer has a superficially similar content of phenol to white wine, but it's only superficially similar, and we'll get to some reasons why in a minute. On page 2, there's a little bit about wort composition, W-O-R-T. I guess most of you have had 102 and know that that's pronounced wort. At least I hope Mike says that. That's what the books say. It's in all brewmeisters I've talked to say wort. Wort has only 9 to 13% sugar prior to fermentation, and the alcohol ends up at about 4.5 to 7% in the beer. So in that sense, there is a difference. And there is an interesting point regarding the nitrogen. It's been now shown also, Professor Berg and his students have shown by inference and by electrophoresis also, but now some better studies or additional studies with immunological studies of protein have shown that in every case investigated, the protein of the drink, whether it be sake, beer, or wine, reflects the protein of the starting material that was fermented. In other words, the main point is that the yeasts do not contribute proteins to the product. Now, this is a rather important finding for a number of reasons, not the least of which is the autolysis of the yeast is a contributor to champagne flavor during bottle aging and that kind of thing. The significance then, and Mike Lewis and some of his students have added information in this regard. Apparently, when we speak of autolysis of yeast cells, I've always tended to think of it as the same thing as a breakdown of a grape. In other words, autolysis to me meant that the thing popped open and the contents of the yeast cell got out just as grape juice gets out when we crush the grapes. Apparently that's not so, that the cell wall stays intact, at least in the kinds of autolysis that would be involved in normal fermentation, and the cell wall becomes leaky so that the constituents get out, but the constituents that do get out are not proteins, they're smaller. They're either nucleotide fragments, and this is what Mike and his students have mainly investigated, or they're polypeptides that are too small to be considered proteins. So as a consequence, when we have a protein instability in a white wine or in a beer, this protein is derived from the grape or from the barley or other grain constituent in the beer. And I think that's important because it helps explain why certain grape varieties give a lot more trouble than others and so on. The nitrogen of beer is quite important in at least two ways. They want nitrogen of a fairly large molecular weight, at least a polypeptide, maybe a small protein, in beer because this is important in head retention. Now, it's quite interesting that in champagne, which are called in German Schaumwein, which means foam wines, actually we don't expect them to foam. In fact, if you poured champagne in a champagne glass and this is the surface of the liquid and you got a head on it like beer, I think you'd find your champagne consumers were horrified and put off by this. So we want a bubble display, and maybe we want a light bubble ringing at the glass perhaps, but you realize it's quite different from beer. In beer, and now visualize this as a beer glass, you want a rather heavy, creamy head on the beer. And if it doesn't have it, it's not considered good beer. Certainly if it looked like champagne and was bubbles formed and then broke as soon as they got to the top, it would be considered bad beer or at least off character. Well, this creaminess of the foam or the head of the beer is related to protein content. And not only that, but there is a characteristic of beer that is considered important, and in breweries they call it cling. When you drink the beer or after the beer is poured out of the glass, there's a lace of foam that stays on the glass, and this cling or lacy foam is also considered part of the aesthetic character of beer. And again, if it didn't happen, why the beer would be considered undesirable. So for these reasons, and perhaps also for some carbon dioxide retention value, which might act in champagne too, the protein content, or at least large peptide content of beer, is considered a positive value. Whereas in wines, particularly white wines other than sparkling at least, protein is invariably undesirable if it makes any known difference at all. So either it'll cause precipitate and therefore be undesirable, or has no valuable effect that we're aware of. Yes, Jeff?
I was under the impression that dextran and polydextran also.
Well, it has an effect apparently, but it isn't that important an effect. It has effect on body of the taste and the mouth filling effect and so on, but the evidence is it doesn't have too much to do with the head composition. It's possible to take a dextran solution, for instance, and water, and you can't whip it up in any way. I've done it myself, in fact. You can't whip it up in any way to give any sort of a beer-like head, so that maybe it contributes with the protein, but you can't make it without the protein. You hear all about the water is what makes it good and so forth, and part of this is because of the pH and the calcium content that regulates the solubility and the shape, more or less, of the proteins in solution. So that you can buy salts to add to waters, or you can send your water in to several labs that do this sort of thing. They'll analyze the water and tell you what you have to either put in or take out to make it as good as Olympia's or anybody else's. I'm not so sure whether they're 100% successful, and certainly it's a lot more economical if you've got a great spring that the water comes out just right in the first place. But there is an example here. 734 parts per million calcium sulfate and 610 parts per million calcium chloride is an example of what has been recommended. And this also influences the lace and the cling as well as the head, so that it isn't just protein, it's protein as modified so that it will give these proper characteristics. The hop picture is pretty well outlined in your paper, and I don't think as much we need to say about it. It's pretty unique to beer, and therefore I think I'll skip over that. The only thing I will say is that it has worried me as a drinker of a fair amount of beer that these compounds look very, very similar to the if someone ever wanted to make a case, I think they could probably, if it were not for the grandfather clause of knowing that beer's been consumed for a long time with apparent safety, I'm sure that you'd have an awful difficult time introducing the use of hops into beer, and we may yet have trouble in keeping it there. The haze formation, then, is the main way that beer studies overlap with wine. And I think it's quite instructive then. We said that the protein's important in beer and comes from the barley. The protein is probably unimportant in white wine and comes from the grape. So the treating methods that we would commonly use with wine is to remove the protein as completely as possible, and with beer, remove the tannins as completely as possible. And the tannin that's present in white wine is at a level where it does contribute favorably to overall flavor. If you remove the tannin completely, and it's not easy to do without doing other drastic things to aroma and so on, but if you do, clearly you have decreased the slight briskness or slight astringency even of a white wine, and cut the bitterness. And you do want a little bitterness. In beer, of course, you've added a lot more through the hops, but in white wine, that little touch of bitterness is useful in making the wine taste not flat and full. And they find the same thing in beer. If they take the phenol content below about 30 parts per million, they do find that the quality of the beer is decreased, and it doesn't taste as satisfactory. So they can lower their tannin content to around 30 parts per million, and it's probably favorable, at least in the formation of haze. Whereas we wouldn't want to lower our tannin that much, but we could lower our protein to 0, apparently, without hurting the quality of the product and improving its stability as far as haze formation. Now, you've heard about chill haze in beer, and those of you who've taken 102 probably know more about it than I do, but the basic idea is that chill haze is a transient turbidity that forms when you refrigerate the beer, which disappears as the beer warms up. And they, for a long time, made an important, they thought, distinction between what was called permanent haze, that wouldn't clear up when you warmed the beer, versus chill haze. But it's pretty clear now that they're just stages of the same thing, that the same kind of precipitate, once it gets big enough, just won't go back into solution any longer. Now, what is the nature of this precipitate? Well, the chill haze precipitate has been studied in considerable degree, and it runs about 25% phenolic material and about 45 to 60% protein, with the rest being carbohydrate, which can be 0 to 25%, and a little bit of ash and a trace of nucleic acids. So the main significant constituent is protein and phenol, and the phenol is generally less than the protein in the beer, whereas might not be so in wine, depending on the bentonite treatment that had been used and so on. And the picture seems to be this. When you boil the wort prior to fermentation, you've denatured the proteins pretty completely and also hydrolyzed quite a few, so that although there's still polypeptide material there, it's considerably denatured, and the heavy ones would be thrown out of solution, as would the large polyphenols, because the polyphenols that are capable of precipitating with protein would be reacted with this denaturing protein. You'd get fibrillar protein. This would react with the tannin, and the wort, after boiling, would be pretty much freed of readily precipitating protein and or tannin by a combination between the two. Then, after fermentation, if the situation changes, and of course the temperature would go down, then we can form a haze, and the haze would be between the biggest of the proteins and the biggest of the flavonoids or other tannin-like molecules. All right, if you get either of them changing in size, you can affect whether it comes out or not. So the proteolytic enzymes have been used to prevent or delay the formation of chill haze by breaking the polypeptides into smaller units. But of course the beer people were stuck with the fact they wanted peptides to give the head and the cling effects. So they couldn't completely digest the protein. So the trick was to break them just enough that you delayed chill haze formation without harming the other details. Now they used to talk about, I remember a paper or two that said that after you use chill haze enzymes, proteolytic enzymes to prevent chill haze, the peptides reformed and you got Haze later. Well, that shook me up considerably as a former protein chemist, because the energy requirement of synthesizing a peptide bond is pretty high, and unless you had a lot of free ATP and a few biochemical ribosomes and other things in there, I don't quite see how you'd get synthesis or resynthesis of small peptides into large proteins. And they soon quit talking about this, realizing, somebody pointed out to them, not me, that it was a stupid way to put it. So what was happening, apparently, was that the phenols were oxidizing, polymerizing, and then they got big enough to be capable of precipitation of the smaller polypeptides. So that having made smaller polypeptides, it took a bigger tannin to bring it out of solution. But giving some oxidation, you generated the bigger tannin, and it did come out of solution. So this, I think, has instruction from comparison with wine as well, in that then in the wine we tend to have the reverse situation. In red wine we have so much tannin there's no detectable protein left, and in white wine we tend to have excess protein and not enough tannin. Therefore we can use tannin fining to lower protein content of white wine, and the reason we commonly speak of gelatin tannin fining is that the gelatin has a more predictable, it's a linear molecule, a more predictable reaction with the tannin. So commonly you add excess tannin, hopefully throw out all the protein of the wine, and then to make sure you don't have excess tannin left, you add enough gelatin to bring out the remaining tannin. Now you know it's possible to overfine and leave gelatin in solution, and so that's one reason why it's common to follow that treatment with bentonite, to make sure the bentonite takes out the gelatin. So it's a complicated procedure, and nowadays we tend to use only bentonite since it's the protein we're trying to remove. But it does seem to me that it makes a good story and a clear understanding of why we should keep up with the beer literature and contrast what they find with what we understand about our product. The mechanism and kinds of precipitates are given to some degree, and your references, I think, would make a complete study if you wanted to go further into the situation with regard to beer. With regard to tea, we've already mentioned something about how it's made, and again, the manufacturing methods are pretty well outlined in your notes. We've mentioned the theaflavin production. And note again that it seems to be dependent on the gallocatechin type structure. In other words, it seems to require a pyrogallol B ring, and it might be that miracetin and other compounds can do this same sort of thing. Similar compounds have been produced in the test tube by reactions of this kind with some compounds other than catechin derivatives. So we assume that it takes one trihydroxy B ring and then a dihydroxy or possibly even monohydroxy B ring to form this dimer of this tropolone type, and these dimers then have colors, visible golden colors, and evidently flavor effect. We've already said that any dimeric flavonoid should be a tannin in the astringency sense, and although this hasn't been well studied in the case of the tea products, it has been rather well shown that they do relate to the quality of the tea. So the brisk flavor of the tea is related to the theaflavin content. And the better quality teas have a higher theaflavin content and a greater briskness. So that the correlation of chemistry with quality is perhaps better, at least from a phenolic viewpoint, with tea than with any other product. And on page 5 there's a small table indicating some taste testing data that shows some of these correlations. The other group of compounds that occur in tea are called thearubigens, and the thearubigens are much more heterogeneous. At first they were thought to be further oxidation products of the theaflavins, and the feeling was that if you let oxidation go too far, you converted the desirable golden theaflavins into undesirable muddy brown, reddish brown thearubigens, and that's where the name comes from. The ruba means a reddish color, and the flav, of course, means a yellow color. The thearubigens, however, now have been shown to be largely leucoanthocyanin derivatives and having a large molecular weight. So there's several compounds in this type class, not all of them large molecular weights, and the range of molecular weight given is from about 700, which would be the dimer, to 40,000. Nevertheless, generally speaking, the less you have of these compounds, the better. So the higher proportion of the phenols that you can keep in the theaflavin form and the lower in the theorubigen form, the better for the black tea quality. These do contribute astringency and what's called strength to tea, so that the good rich brew of tea has a fair amount of theorubigens, but still the quality would mainly reflect high theaflavin content. Again, coming to the aroma story, there is pretty good evidence that carbonyl compounds are formed in tea, and there's better evidence in tea, but remember the situation is quite different. You start with a leafy material that may be 30% phenols on a dry weight basis, has a very low moisture content, starts at about 75, but by the time it's withered, it's down to about 55% moisture. So you have a very concentrated solution of phenols and a relatively low content of amino acids, so that you have a much better chance of converting a sizable fraction of the amino acids that are there, and also perhaps the lipid material. And this beta ionone contribution to a violet character is perhaps important, but how much tea have you had that made you think strongly of violet? So it's still somewhat up in the air, as a lot of this sort of thing is to just exactly how much does this compound contribute to the overall flavor quality. Nevertheless, we have some pretty good inferences that phenols, both directly and indirectly, are very crucial to tea quality. Well, I think I've said much about defining agents and tannins. We might come a little bit to how to lower the astringency of 2-tannic and also bring in why do the anthocyanins only penetrate a short distance into the wood. Well, I think this is obvious to you now. The anthocyanins, except in extremely young wines, become polymers, and the polymers are not going to diffuse so readily into the wood. Now, you could argue that the tannins of the wood are also polymers, and I'm not even sure, within limits, this statement is true. But also, if you take barrels in which red wine has been stored and cut the staves, you'll find that the red color is a fair distance into the wood, as deep as 1/4 of an inch. And that being so, then I'm not so sure whether you're just extracting tannin from a much deeper layer. It would depend partly on the condition of the wine when put in the barrel. If it's put in quite new with still a reasonable anthocyanin content, then I think the anthocyanins can penetrate about as deep as you're extracting tannin. We've been trying, but so far haven't succeeded, to take barrel staves and use cross-cut barrel staves and use pH indicators to detect how deep tartaric acid has gotten, since the pH of wood's about 6 and the pH of wine, of course, is about 3. We had hopes of doing that. So far, I haven't been able to get the right combination. Whenever I put the pH indicators on the wood, then the absorption reactions of the indicator with the wood change the picture enough that I haven't been satisfied that I am observing any sort of a boundary between tartaric acid and the rest of the wood. While we're on that point, there is one thing that I think is perhaps interesting. It's been generally found that if you paint a barrel, you don't get the right effect from aging. And when I talk to people, or when I've tried it myself, as to what happens, they're not very clear what happens. But if you put an impervious coating, or if you maintain the barrel in a very high humidity condition, then it seems to me you're going to be getting the barrel wet, a deeper layer. In other words, the wood is air dry into some point, it's waterlogged into some point, and then the intermediate between the two. Well, if you're going to raise the humidity out here, you're going to increase the depth to which you're wetting the barrel, and therefore you should increase the extraction rate, so that painting the barrel or other things may be bad in the sense that they contribute too much extract too fast because you're extracting from a deeper layer. So there are a lot of interactions in this sort of situation that one can't always specify, but that's why when you do something simple like, for instance, recently they've been putting brandies and whiskeys in barrels at a higher proof. The reason being you get more gallons of brandy in, you don't have to use so many barrels. Well, they find this makes a lighter product, and of course it makes a lighter product because anything over 55% alcohol isn't as good a barrel extractant as is 55% alcohol. But another reason, of course, might be that you're affecting how deep you wet the wood by the alcohol content relative to the water content. So a lot of these ancient developed techniques that we use have a number of iffy aspects when you start changing them. We still have about 5 minutes for questions that may have occurred to you meanwhile.
Does the red pigment eventually come back out of that barrel?
Well, some will. If you put a white wine in it, you'll wish you hadn't. So to that extent, some does come back.
But that interaction with the oxygen in that layer there, the two of them meeting, will those be pretty well timed?
Well, and that's why I showed at the meeting yesterday that stave. We did have a stave that had a blackish layer here. And I think that's from the reaction of the wine constituents with the air to make polymers that are big enough that they can't come back out again. And certainly there is a tendency in that regard. So I use that as an argument for saying that oxygen as such doesn't get to the side of the barrel. And if oxidation products get back, I think they're relatively minimized compared to the amount of oxygen that came in because they are fixed in the wood by being polymers. And it wouldn't necessarily have to be wine, you see, because if you extract gallic acid as gallotannins from wood, they'll take up oxygen too. So if you wet the wood tannin, it would serve as an oxygen scavenger even if the barrel was full of water. And I think this is one reason why the ships carried water on board in barrels. Water would, quote, stay sweet longer, unquote, in wooden barrels than in particularly oak barrels, something with some tannin in it. All the good barrel materials have high tannin content. Redwood, I shouldn't call it a barrel material, but a wooden tank material. Redwood, oak, cypress, these things have unusually high tannin content. Yes?
This is in reference to something you said yesterday. Based on the experiments on ullage that you referred to, what do you think of the argument that when you roll your barrels on the side, you're going to get a partial vacuum?
Well, I think it's true. I mean, I'm the last one to argue against observations made by winemakers who are pretty good observers generally. So my reaction is that the way I visualize the thing is that if you want to roll the barrel and not make up ullage, then that's all right, as long as the ullage stays small enough that the wood is completely wet. But if you get a dry spot at the top, then that dry wood is almost no barrier to oxygen penetration, because it turns out that by data available in the literature, oxygen will penetrate dry wood about 80% as fast as it will still air, and that's very fast. So that once there's a dry spot, you won't hold your vacuum. So as long as there is a vacuum, that proves to my way of thinking that what I'm saying is true, that air does not penetrate wet wood very well, otherwise you couldn't maintain a vacuum. And as long as the vacuum is good, that means the wood is all wet and you're not running any great risk. So it would seem to me if you roll only for whatever the time is that that'll stay wet, which may be a year, then you're all right. If you wait 3 years, I think you're going to have a lot of vinegar on your hands.
With the structure of wood, as you were describing with tylosis, that it wouldn't take too much ullage space before you'd have a dry spot there.
Well, I would be afraid that it wouldn't, that's right. I'd guess something like 2 liters of empty space would probably give a small dry spot, and once you got a small one, then that's all it takes. And it's also why corks ought to be kept wet, you see. It doesn't take much wet, but it's got to be wet, otherwise it's not a good barrier to oxygen.
Dr. Singleton, doesn't gelatin also say 3 to 5 months?
Maybe so. You see, I don't know what they do say. I've heard people say longer, but is that right?
3 to 5 months, I think.
Okay, great. So then I think you'd be perfectly safe. Well, the other class is upon us, and I think it is about time, so I guess we'll consider this it, except for the final, which I believe is Tuesday, isn't it? Yeah, 4 to 6. Lovely time of day. If you have any questions that haven't been covered, I'll be glad to talk to you individually. And if you wanted a copy of that paper I mentioned last night and don't have one on some aspect